Good evening. Uh, so we'll talk about the many body methods in quantum chemistry. So this is the week 6. In this week, I guess you have learned about others letter rules that were required, where the determinants on the Brian Kate sites are different by a single occupation or double occupation. There, then you have learned about the basis sets. Uh, so you have learned about the basis sets, like what is polarization function and diffuse function that I also talked about in our previous live session. And you have now will come to the game of correlation picture where the correlation will be important. Though Hartree-Fock recovers around 98-99% of the total energy, but the all the chemical phenomena or chemical reaction happens within that missing energy region. So where the correlations become very important. So you learn about MP2 couple cluster and all that. So today also in my slides I will talk about the electron correlations. So so my intent in this live session will be to discuss the um, Gaussian product theorem that I have told about in my previous live session. I will solve plenty of assignment questions that I have accumulated, and in the later course, I will try to talk about the electron correlations method from the slides of Professor David Sale. So, without a further ado, let's start. So, we'll first start with this simple problem. So actually, to mention this, these problems are actually taken from IIT Bombay's CH560 course. So this is the same course that is run in here at IIT Bombay, and from there I have taken these questions. So this is a very simple question. It asks that if two operators A and B are Hermitian, that means your A dagger is equal to A and B dagger is equal to B. So now we have to check whether the commutator of A and B they are Hermitian or not. So this is a very simple problem, but let's go through step by step. So now you have to answer that this whether this will give me back the same commutator or not, right? So for that, so the commutator AB is nothing but AB minus BA dagger. So then this is AB dagger minus BA dagger. Now you know that AB dagger is B dagger, A dagger. These things we have proved in the one of the live session where we have talked about the matrix multiplication and linear algebra. So now we can see that everything is coming very handy. So now this is A dagger, B dagger. Now as A and B are individually Hermitian operator, so this reduces to BA minus AB, which is minus of AB minus BA or minus of AB. So this is certainly not, I mean, AB commutator conjugate is certainly not equal to AB. This is minus of the commutator. That's why it is actually, this is called the anti-Hermitian. This is anti-Hermitian. This is not Hermitian. So this is not Hermitian. Now they have asked whether so the condition for which the product of these two AB will also be Hermitian. That is also very straightforward. So this asks that AB dagger is actually BA dagger. So this will be only Hermitian if your BA is equal to AB, right? And which is nothing but your AB minus BA is 0. So that means A and B must commute. So when A and B commutes with each other, then the AB that is here, that will be Hermitian. So we have solved this question. Now here's the second question. This is a bit trickier, so it will take some time to solve this. So I'll ask you to pause this video, or you should give it a try first. Then we'll see that whether you can solve this or not, or we can solve this here or not. Okay. So let's read the question first. It says that prove that e to the power I alpha x, where your alpha is a scalar, and x, y, z, they are basically the Pauli spin matrices. So these spin matrices we have already discussed. And e to the power I alpha x times z time e to the power minus I alpha x is equal to, you have to prove that it is equal to z cos 2 alpha plus y sin 2 alpha. Now, if you blindly expand this e to the power I alpha x in terms of Taylor series expansion and e to the power minus alpha x, you can eventually get it, but there is one trick that you have to remember. So let's first discuss the properties that these Pauli spin matrices have. So we have already discussed in previously, so here just we'll note it down for our derivation purpose, or you can go back to that previous session, and from there you can learn it. So the properties of Pauli spin matrices. Okay. The, the first write it down. What is x, y, and z? So x is 0, 1, 1, 0. These are not required, this matrix. So I'm just writing it down for your convenience. And y is 0, minus I, 0, and z is. So whatever the properties I am going to write, you can verify from these matrices. This is up to you. The first property is that x square, y square, and z square, they give you the identity matrix 2 by 2. And the second thing is that like every pair, for example, x, y, this is the anti-commutator sign. So this is nothing but x, y plus yx. This is actually 0. Now you have yz and zx. All these on anti-commutators, they are 0. Right. And another property, x, y, when you take the matrix multiplication of x with y, you get I, z. And yz, ix, and zx give you iy. So these are the three properties that will be required. Now, let me show you one thing. For any matrix, so e to the power I alpha x. Now, if you expand this exponential and provided that your x square is equal to 1, like any matrices which follows this property where x square is equal to 1, you can write down, so you can actually write down this e to the power e to the power I alpha x, or e to the power minus I alpha x in terms of cos and sine function that I'll show you. So, so e to the power I alpha x, how you are going to write it? From the Euler's theorem, you can write it, uh, or not Euler's theorem, we'll write it through the Taylor series expansion. So, which will give us 1 plus I alpha x plus I alpha x square 2 factorial I alpha x cube 3 factorial. Now, if I'm writing all these terms, you will see soon. Now, you can write this as 1 plus I alpha x, right? And this term I square is minus 1. So you have minus alpha x square 2 factorial. Then here I square is minus 1, right? And you will be left with another minus I. So this is minus I alpha x divided by 3 factorial. Then again here I square I to the power 4, so that is plus 1. So now you have alpha x to the power 4 factorial. Now if you club all these terms together, e to the power alpha I alpha x, then you have 1 minus alpha x square divided by 2 factorial plus alpha x to the power 4 divided by 4 factorial. So if you see the term, so alpha x square divided by 2 factorial, alpha x to the power 4 divided by 4 factorial. And you have other terms like minus alpha x to the power 6. So this will start from minus dot 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 this term. And you have other terms like I alpha x. So if you take common I from there, so now you have alpha x and alpha x cube divided by 3 factorial plus alpha x to the power 5 divided by 5 factorial, and so on. So this is the general thing, right? Now, if you have a property like x square is equal to 1, then you can see the first terms in the first parenthesis that reduces to minus alpha square divided by 2 factorial plus alpha to the power 4 factorial minus dot dot dot. Then you have this plus I. Then you have alpha x minus. So you have, so you can take out x common from there, right? Because now you will have alpha cube x, right? So now you will have alpha cube x. So you can take common this I x here. So now you have alpha cube 3 factorial plus dot 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 another. Now if you look at this term, this is very similar, or you know already, this is the expansion of sine alpha. in the polynomial series. Oh, sorry, this is the cos alpha, and you have ix, and this alpha minus alpha cube. This is the actually the polynomial expansion of sine alpha. So you can write. So now you can write e to the power I alpha x equal to cos alpha plus x, or ix sin alpha, e to the power minus alpha x cos alpha minus ix sin alpha if your x square is 1. Okay, now let's get back to our problem. So our problem was e to the power I alpha x, then you had z, and e to the power minus I alpha x. So now we can write this e to the power I alpha x as cos alpha plus ix sin alpha, and you have z ix sin alpha. And these you can write it. So these alphas are the basically your scalar number. So you can write it as z cos alpha. And here please maintain the in whatever way the x and z, like the order you have to maintain here. You cannot just write zx because they are matrices. So here you have to write I x z sin alpha. So we have done this multiplication only. We have other multiplication. So here we have ix sin alpha. So we have ix sin alpha cos alpha. Yes. So now we can further multiply this, and we'll have z cos square alpha and minus izx sin alpha cos alpha. Then we have ixz sin alpha cos alpha, and at last we have this I square and I square, that will be minus, and there is another minus here, so it will be plus, and you are left with xzx sin square alpha, right? Let's further simplify things. So now, so how you can write this xzx, right? So xzx, so zx, it commutes with x, right? So it is nothing but xz from the second property. So you can write xzx as minus x square z. So I'm writing x z. So this xx becomes x square, and x square is 1. So this is minus z, right? So we have z cos square alpha minus z sin square alpha. Okay. Now here you can take common. So this xz and zx, so they So you can take common I here, or you can just simply do Zx is equal to, let me see. So this is Zx. X. You can just simply write this xz as minus zx, right? So now you simply have I zx to sin alpha cos alpha. So finally you have z cos square alpha sin square alpha, and you have I zx minus I zx. So I have told you that zx is nothing but Iy, right? From this property, you can see zx is Iy. So you have Iy and 2 sin alpha cos alpha is sin 2 alpha. And cos square alpha minus sin square alpha is z cos 2 alpha. And from here you have y sin 2 alpha. And that's what we have been told to prove, right? Z cos 2 alpha, y sin 2 alpha. This is e to the power I alpha x z e to the power minus I alpha, right? Yes. So now you can see this problem, but we'll solve this problem in later after discussing the electron correlation from the slides. So here it is mentioned that consider the matrix eigenvalue equation for the case of configuration interaction with the Hartree-Fock determinant psi h and singly excited determinant psi a, doubly excited and triply excited determinants. So you all know this in configuration interactions, it's a linear problem. So you write the total wave function as a summation of your all the excited determinants, right, including your Hartree-Fock. So in this case, your basis is the n electron determinants, right? So we'll actually in the slides we'll see that how this forms a basis. So now it has been told that write down the explicit form for the interaction matrix. So we have to write the Hamiltonian in the basis of this excited state determinant. So we have already practiced this in our linear algebra live session. So we have to write down these matrix elements and we have to indicate the vanishing and non-vanishing terms. So I think you have already heard about the Brillouin's theorem, and if not, maybe in this week or you will be learned about the Brillouin's theorem. So it will come handy there, and then we'll calculate the dimension of matrix, which is the easier part. So we'll discuss this problem in the later time. Before that, so now we can discuss the introduction to, okay. So before this, we'll do another job that is left is the proof of the Gaussian product theorem that I have already promised in the previous lecture. So let's prove that. So in the previous session, while talking about the basis sets, there we have come across about the Slater functions and the Gaussian function. So Slater function is the real function, but you denote them as a you try to mimic them with the help of a multiple Gaussians. So you take a linear combination of Gaussians to form a or to mimic the Slater determinants. And we have also shown from the graph that if you increase the number of Gaussian like H2O1G, H2O2G, and H2O3G, if you remember the plot, so there you can see that it actually enhances the or in near the nuclear region or in the longer region, it actually better mimics the actual Slater. Right. So now why the Slater was the problem? Because if you use the Slater, your evaluation of the two electron integral becomes very difficult. But in case of Gaussian, you have force center two electron integral lambda sigma force center two electron Gaussian. So this if this is a Gaussian, this is a Gaussian, then actually the product of two Gaussian gives you one Gaussian that is centered on a different center from the individual position. Right. So that will prove that if you take the multiplication of two Gaussian, that actually gives you back another Gaussian in different center. Right. So uh, let me take that slide. So here is the problem statement. The statement goes like you have a Gaussian that is centered on A and the exponent is alpha, and you have another Gaussian which is centered on B and you have another like the exponent is beta. Now you can prove that if you take the product of these two Gaussian, this actually gives you another Gaussian with the exponent gamma, where gamma is the alpha plus beta. So the sum of the individual Gaussian exponent. And this new center P is basically the alpha A plus beta B divided by alpha plus B. So we'll prove that. Okay. So and here you can see an constant K. So you have GPX is equal to G Gaussian at A and Gaussian at B, right? And this K, or we can denote it as KAB. So we'll come to see that whether I have given this name KAB. So this is actually your e to the power minus gamma x minus p square is equal to GAX GBX, right? So KAB is GAX GBX divided by e to the power minus alpha x minus p square, right? So let's give it equation number 1. We'll come to this. Now take the right hand side of this equation. So GAX times GBX. So this is e to the power minus alpha square times e to the power minus beta x minus b square. And you can write this as minus alpha x minus a square minus beta x minus b square, or let's say minus e. Right. So I'm exponent, I'm writing this. This E is basically, so the E is basically alpha x minus a square plus beta x minus b square. From here, if you take common, this is minus. So this I am denoting as E, capital E. Now let's expand this. So now you'll have alpha x square minus 2 alpha, let's say we'll have x square minus 2ax plus a square plus beta x square minus 2bx plus b square. Now you'll have alpha x square. So you can take common this x square. So you will have actually, so from this term and this term, you'll have alpha plus beta x square, right? And from here, this and this, you can take common 2x. So now you will have alpha a and beta b x. And the remainder part, alpha a square plus beta b square, right? So your E reduces to this. Now, given this information that your P is alpha A plus beta B divided by alpha plus B, and gamma, the total exponent, is alpha plus beta, let's expand this term like this Gaussian GPX actually. So let's expand this term e to the power minus alpha plus beta x minus p square, right? So this is your total exponent and this is centered. So this is the new center, right? So let's expand this, or we can call this as this total thing, we can call this as P. So actually the P becomes, or I shouldn't say P because we can say this P dash. So this P dash is alpha plus beta x minus p square, right? So now what you have, alpha plus beta x square minus 2px plus p square, or you have alpha plus beta x square. Look at this term and this term. Now you have 2 alpha plus beta px, right? Now in place of p, you put this, the value of the p that is given. So you can put alpha a plus beta b divided by alpha plus b. So I'm in place of p, I'm putting the value of the capital P, and now you're left with this x. So you can see this term will get cancelled, and you have the other term, that is alpha plus b, alpha plus beta times p square. So let's write down. So you have alpha plus beta x square minus 2 alpha a plus beta b, or I should write it in the next. I'll try to write it here. Alpha plus beta square, sorry, x square minus 2 alpha a plus beta b x, and you have this alpha plus beta b square, right? Now from the equation 1 you can see that KAB is equal to the individual product divided by the e to the power minus gamma x minus p square. So this is your numerator and this is your denominator term, right? And these two terms, this term and this term, and the first term and the first term, they get cancelled, like they get cancelled, right? So there will be some remainder term. So what will be that term? So from the equation 1 we can write KAB is equal to, so what is the term here? Alpha a square plus beta b square, right? So now you have e to the power alpha a square plus beta b square. Now you have alpha plus beta capital P square, right? So minus alpha plus beta capital P square. So alpha plus beta, and put the value of P here, alpha A plus beta B divided by alpha plus beta, right? So you have alpha A plus beta B whole square divided by alpha plus beta square. So this is the whole term. Now one of the alpha plus beta will get cancelled. So now you are left with alpha A square plus beta B square minus alpha A beta B divided by alpha plus beta. Now just simply do the multiplication, alpha plus beta. So it will be alpha square a square plus alpha beta a square, alpha beta b square, and beta square b square. And from this quadratic term, it will be minus alpha square a square minus beta square b square minus 2 alpha beta a b. This term and this term, and this term, two term will get cancelled. Now you have e to the power, you can take common alpha beta. Now you have a square minus 2ab plus b square divided by alpha plus beta. So now you have e to the power alpha beta a minus b square divided by alpha plus beta. Now you can see that why this KAB nomenclature. So this alpha and beta are basically constant, and the position, this A and B in the Born-Oppenheimer picture that we are dealing with, so they are also constant, right? So this whole KAB is a constant. So given two Gaussian, you can actually calculate this KAB. So finally, what you are getting, you take this Gaussian GA, GB, X that is into different center. Now what you are getting, KAB times GPX. So this is the Gaussian product theorem. So you can pre-compute this KAB and you will get a new Gaussian, right? So what happens is that your this two electronic antisymmetric integral, so this mu nu, this gives a different index, uh, let's say mu dash or something, and here this gives a lambda dash. So you actually from a four center two electron integral, it reduces to a two center two electron integral, and the computation of these integrals become very faster. So that's why it's globally or conventionally all the quantum chemist people use this Gaussian type basis set, right? Okay, so now we'll prove this or we will solve these questions after discussing the electron correlation. Give me a moment. So now we'll discuss about the introduction to electron correlation. So here it says that the molecular orbitals are not real. Molecular orbitals are the eigenvectors of the Fock matrix in Hartree-Fock theory. Hartree-Fock is just an approximation, even if a complete basis set used, right? So you have already learned that Hartree-Fock is an approximation because Hartree-Fock seeks the best determinant possible for the ground state or whatever the state you are interested in, right? Because there are two reasons. It's not so even if you use a complete basis like infinite basis, then again your Hartree-Fock is a assumption, right? It assumes that the wave function can be written as one Slater determinant. So this is wrong. So that we have seen in the configuration interactions already that if there is a two electron, then so there is two electron that is interacting, then the single determinant is not the correct picture or the accurate picture. This is just an approximation. It assumes that each electron interacts with an average charge distribution due to the other electrons. So this is wrong because there is instantaneous reaction or interaction between electrons, right? So if there is if there is three electrons, so this electron is actually sees the electron average electron cloud from these two electrons. But in real picture, the interaction is between this electron and this electron. Right. But so this is an approximation because your Fock operator, your Fi is the Hi plus summation of your J chi J. So if this is the second electron, so then you have chi J star 2 integration 1 minus p I2 because I'm writing the Fock for the ith electron, or I should have written 1 here. So pi I2 r I2 chi J2 theta 2, right? So here you can see this is an average interaction. So this is an approximation, right? So here comes the electron correlation. Electrons repel each other according to the Coulomb's rule and with the repulsion energy Rij inverse, that is 1 by Rij. In the atomic unit, this is the way that the two electrons interact with each other, or actually they repulse each other. Hartree-Fock replaces this instantaneous electron-electron repulsion with repulsion of each electron with an average electron charge cloud that I have just mentioned before. This introduces an error in the wave function and the energy. The energy error is called the total correlation energy. Right. So the correlation is nothing but whatever is there in the Hartree-Fock. So the E exact minus E Hartree-Fock. So whatever the shortcomings are there in your Hartree-Fock picture, that is called the correlation, right? Because in Hartree-Fock you take the average electron approximation, so then you actually don't get the electron correlation. But again, I'll come to this point. This is a very common misconception that people has, that the Hartree-Fock doesn't contain any correlation, but this is not true. That I'll come later. So the error in the total energy is about 1 electron volt per electron pair in a bond or lone pair. So this error is around 1 electron volt per bond or lone pair. So this is in terms of chemical application, this is huge. So one has to take care of the electron correlation. Dispersion forces are due to the electron correlation. Expect Hartree-Fock to fail very badly for van der Waals complexes. So the dispersion force is nothing but the dipole-induced dipole interaction, right? So, so this is a very, uh, I will say that. So in dispersion forces or van der Waals attraction, what happens is that there is an interaction between. So even if you have a symmetric charge, so in a very fraction of second, the electron densities are not distributed equally. So there is a kind of dipole present. So in an average, so you can see a zero dipole, but there is some instantaneous dipole. So this dispersion is basically the interaction of this induced dipole with the with the with the another dipole. Now, if your Hartree-Fock don't averages out or smears out this interaction, so it will not see this interaction. So there the Hartree-Fock will fail very badly, and it is actually been proven already. Now comes the correlation energy. The correlation energy is defined as the difference between the true energy and the Hartree-Fock energy in a complete basis. So the correlation energy is E exact minus E Hartree-Fock in a infinite basis. But usually we don't know the exact energy, right? But sometimes we compute the exact energy for a given one electron basis. So that is basically your full CI or higher order couple cluster, depending on like various factors, but you can consider the full CI in a given one electron basis. This lets us compute the basis set correlation energy. So here's a very subtle differences. So the E correlation is basically the E exact minus the E Hartree-Fock at the infinite basis set. Now the E correlation basis, this is basically the E exact in the given one electron basis minus the E Hartree-Fock in that given one electron basis. Now why it's called a electron correlation? So the Hartree product, this chi j times chi k is completely uncorrelated in the sense that the probability of simultaneously finding an electron 1 at x1 and electron 2 at x2 is given by the modulus of this psi Hartree-Fock, right? So this is the probability of finding the electron 1 in x1, electron 2 at x2, and electron xn at xn, right? Now, if you see this probability, this is nothing but the individual probability of finding the electron, and you take the product. So that means the electrons are are basically behaving in an independent way, right? So which is the probability of finding electron 1 at x1 times the probability of finding the electron 2 at x2 and the product of these probabilities. This makes the Hartree-Fock product an independent particle model. So because in the Hartree-Fock you are taking the single Slater determinant, so you don't see the effect of electron 1 on the position, the effect of position of the electron 1 to the position of electron at another position x2, you can say. That's why the electron correlation is not there in the Hartree-Fock. Now comes this interesting fact. Hartree-Fock is usually defined as uncorrelated. However, the electron motions are no longer completely independent. So this is the misconception that the Hartree Fock is totally a uncorrelated method, but it's not. So let's see the things. For two electrons with different spins. So so we have two electron R1 and R2, and they are in two different orbital, psi1 and psi2, and their spins are different. So one has a alpha spin and one has a beta spin. The probability of finding the electron 1 at R1 and electron 2 at R2 is given by this probability, this times dr1 dr2. So this is nothing but if you take the integration from so you have to take the whole integration over this d omega 1 and d omega 2, right? So now you take the psi square, and now this alpha and beta, so what you will have actually, so what is this? This product is basically your psi 1 psi 2 minus psi 2 psi 1. So this is a Slater determinant, right? So now you have here one electron 1, electron 2, electron 1 and electron 2, and you just assign the alpha spin and beta spin. Now if you take the product psi mod square, so here is two terms, so now you will have another terms also, right? So or let me write it explicitly. So you have psi 1 alpha and you have psi 2 beta. I am not assigning the sign here, and you have minus psi 2 beta psi 1 alpha, right? Now if you take the psi mod square, so if you, the psi mod square is basically psi star, so this is your total psi star psi. Now you have to take this, there will be four terms because here is two terms here, so if you take the multiplication you will get four terms. So here you will have psi 1 star, so you will have terms like psi 1 star and alpha and psi 2 psi 2 beta, this kind of terms will be there. Now as this alpha and beta they have the different spin, they are actually going to zero. That's why they are only mentioning two terms here, 1 and 2, because your alpha and beta they are the different spin, right? The only term that will survive is that the psi 1 alpha, this psi 1 r1 square and psi 2 r2 square. So these two terms will survive, right? So here you can see the electrons are uncorrelated. Now why? Because for, so electron correlations means that electron are never going to be at the same position. So now if you put r1 is equal to r2, so if you put here r2 is equal to r1, or here if you put the r2 is equal to r1, so it actually allows you to put r1 is equal to r2, so you will get a probability, right? But in the actual picture, the two electrons, because of their charge, the negative charge, they cannot never occupy the same spatial part. So that means the electrons are uncorrelated here. Now what about the same spin? So now let's see. Yes, so here they have mentioned all the term here. So for two electrons with a different same spin, the alpha omega 1 and alpha omega 2. So this is the probability of finding the electron 1 at R1 and electron 2 at R2, right? So now here you have two terms here. So four terms here. So these two terms are the same from the previous, but because these these terms are not going to zero because they have the same spin alpha and alpha, so they are surviving, not like the previous terms here. So they goes to zero because your alpha and beta were different, and if you take the total integration spin integration here, so you'll get zero here, but these terms are surviving here, this term and this term. Now if you put that R1 is equal to R2, you can see that these exactly all the terms will get cancelled and you will get R1 is 0, and which is the thing that you should get. So no two electrons with the same spin can be at the same place or Fermi hole. Same spin electrons are correlated in Hartree Fock. Different spin are not. So Hartree Fock is not a total uncorrelated picture. It actually correlates the electrons with the same spin, but it doesn't correlate the different spin electrons. I think it's clear. Now the n electron basis, this we have already discussed. A collection of atom-centered Gaussian functions can be used as a basis for expanding the one electron function. So far, so in the Hartree-Fock picture, you have chi1, chi2, chi n, right? So each of these chi1, chi2, these are one electronic function. So these one electronic functions can be expressed in terms of atom-centered Gaussian. But we need to solve the Schrodinger equation for the n electron system. So now what can we use as a basis for the expanding this psi electron here? So now you want to solve this electron some E psi. Now this is a n electron function, right? So what you are going to use? Slater determinants are proper n electronic basis functions. They are the functions which can be used to expand any electron function. So now what is the prerequisite of a basis set to be a complete basis set, right? If you remember from the postulate of quantum mechanics, the eigenfunction of an Hermitian operator actually forms a complete set of bases. Now, these chi1, chi2, chi-n, and all the single doubly excited determinants, they are actually the eigenfunctions of the summation of Fock operator. So let's say you have n electron. So now you have a summation of I is equal to 1 to n. So you try with the two electronic functions chi1, chi2, and you take f1 plus f2, and you operate this f1 on this chi1 and chi2. You will see that this is the eigenfunction of this f1 plus f2, right? And as these Fock operators are Hermitian operator, and these Slater determinants are the eigenfunctions of the one like n electronic wave function, n electronic Fock operator. So that's why Fock operators are a effective one electronic operator, right? So if you take all the sum, then you have a, so they are the, these Slater determinants are the eigenfunction of that operator. So as this Fock operator are Hermitian, these Slater determinant can form a, so they can be a complete set of bases. And that's why this third point is mentioned, the Slater determinants are proper in electronic basis function. I hope this is clear. Now, in the limit of an infinite number of Slater determinants, any n electronic function can be expanded exactly. Now, what other determinants? If it takes an infinite number of determinants to exactly represent the wave function, taking only one as Hartree-Fock, so this is, we have already mentioned, this is a decent approximation. For a given set of MOs, the other determinants can be formed by putting electrons in different orbitals. These other determinants will generally belong to different electronic configuration. This we already have discussed, and there will be a pictorial depiction of the same. Right? So now look at this example. Yes, is a minimal basis of hydrogen molecule. So there are, so for hydrogen molecule you have a two orbital, sigma g and sigma u star, right? So now this is MO. It can contain two electron. It can contain two electron. So now you have a four possible determinants: sigma g2, sigma g alpha, sigma u beta, alpha beta, alpha beta. So here actually the total spin is zero. So it's a singlet state that they are talking about. Now note that the middle two correspond to the same spatial orbital configuration, but a different spin orbital configuration or Slater determinant. So now if you look at this carefully, these two, this is contains with sigma g and sigma u, this also sigma g and sigma u. So they have the same spatial orbital, but that their spin orbital configurations are different. Note also that the middle two determinants can be discarded in any expansion of this one sigma g plus star because of symmetry restriction. So now here you need the orbital or the Slater determinants which gives you this Girardet symmetry. Now if you look at these two determinants, this determinant and this determinant, one is Girard and one is ungirard, and if you take the product it give you ungirard. So this cannot be considered as a Slater determinant to expand this one sigma plus G star. However, they can expand, so this they can be expanding, for example, one sigma G, so singlet sigma U state, right? But not this state. So using symmetry, we only need determinants with the right symmetry. So there are three symmetries that one has to take care. One is the spatial symmetry. So that's Girardet and Girardet and all. And there is this SZ symmetry and this S squared symmetry. So SZ symmetry means, so if you have a, so if you are starting with the 10 alpha electrons and 10 beta electrons, whatever the determinants you are going to generate, they will also have the 10 alpha and 10 beta electrons. So your SZ is a summation of all the SZ of individual electrons, and A square symmetry is basically so if you are starting with a singlet and triplet and all that, so that is a square symmetry. So determinants with values different than the desired state cannot contribute to the total wave function. So of the four determinants, all have ms is equal to 0. That's true. The first and the last are also eigenfunction of a square, but the middle two are not. Then you have to take the plus and minus configuration, and that is called the configuration state functions. And so what is this configuration state function? They are, so in the one of our live session we have talked about that how you can write this a square as a s plus, s minus, and sz. So if you operate this a square on individually in this determinant and this determinant, so your a square will not come the way you want, right? So in that case you have to take the linear combination. So you have to either take a plus combination or you have to take a minus combination. That will give you a uh, you know triplet or single state, whatever the state you are looking at. So that is the part I'm leaving up to you. If you operate this S square in these two determinants, you can see they are not the eigenfunctions of this S square operator. So that's why you cannot take this so this determinant. So in a way, you can take a combination of these two, which will give you this configuration state function, and that you can incorporate as a uh, you know as a other configurations to this singlet sigma g plus. So configuration interaction express the wave function as a linear combination of Slater determinants, right? So usually expansion coefficient, uh, so they are obtained variationally. So these ci phi I, so these phi i's are basically your different Slater determinants. So Hartree-Fock, singlet, so singles, doubles, and all that. So in one of the question that I have already told previously, we'll come to that. So what is complete ci? Arrange all electrons in all possible ways consistent with symmetry requirements. So if you have any symmetry requirements, then so we have already discussed that what are the symmetry requirements for spatial symmetry, S square symmetry, and SZ symmetry in a complete orbital basis set. And this is unattainable. I'll give you some numbers that how much it actually shoots up exponentially, right? Now what is full shear? Arrange all electrons in all possible ways without the symmetry for a finite orbital basis set, right? So with respect to the symmetry, so this is also very costly. So in complete ci, actually what you have an infinite basis, and you have to take care all the n electrons in all configurations. Now we cannot do complete ci, right? So we actually deal with a finite orbital basis set. Even in that basis set also you cannot take all the configurations, right? So let's give you some number. So ignoring S square and spatial symmetry but keeping the SZ symmetry, let's calculate that how many determinants can be formed. So let's say there is a n alpha and n beta. So the alpha spins are of n numbers and beta spins of n numbers, right? In total n orbitals. So then how many ways you can do it, right? So you have total n orbitals. So you can take a nc n alpha times nc n beta. So this is the total number of determinants, right? You have. And now let's look at the numbers here. Let's say you have a number of electrons which is 6 and you have a 10 orbitals. Now if you take the all the possible combination irrespective of the S square symmetry, then you have 14.4 into 10 to the power 3. Okay, that is manageable. Now if you increase your basis set size, so see it's a 1,000 time increase, right? Now in 30, so there is a increase in I'll say 15 14 15 times than this, right? Now so now you check with keeping the 10 so let's keep the orbitals number same as 30 and now increase the number of electrons, right? So see at 6 number of electrons you have 10 to the power 6, and look at this number. If you go to just increase 2 electrons, now you have a 10 to the power 6, right? Now if you do a 10 number of electrons, this number is huge, right? You cannot do any calculations with this number of electrons or orbitals. Like, yes, it is possible, but I'm just giving you that it is very, very difficult to do full CI for, say, greater than 20 electrons. So even 20 electrons will be killing. So this limits that we cannot treat system quantum in quantum mechanics or in full CI level uh, beyond diatomics or something like that. So that's a real problem. Now, what is the solution? And what are the number in the parenthesis that you can see that is lower than your the above number, because here they are taking care of the A square symmetry. So because of the symmetry, so that's why group theory is also very important in quantum chemistry, because group theory, so if you use the symmetry, then your the configuration or the number of determinants that get reduced. So because then you don't care, so you don't incorporate those determinants that is actually going to give you a zero value. So full CI is impractical. About 1 billion determinant is the limit of what can be reached today for full CI computation. This requires a highly optimized computer code. For a determinant basis, this means about 12 electrons in 20 orbitals or 10 electrons in 30 orbitals that we have already discussed is mostly diatomics, right? Need to separate more. So what we can do is that we can separate out more important determinant. So whatever the higher order determinants, they can be less important, right? So truncate the CIs according to the excitation level. So now you have a Hartree-Fock, you have singles, doubles, triples. So you can already, so quadruples, dot dot dot. Now you can see that in singles you excite one electron to another electron, right? In doubles you excite two electrons. So you can sense physically that you have to give a more energy to get the doubles excitations and the triples excitation. So eventually if you go, so you have 10 electrons, there will be ninth excitation, 10th excitation, and they are, you know, very unlikely to happen. So you can neglect those determinants. So that's why this is a truncated CI according to the CI level, right? So the Hartree-Fock reference. So here we will be discussing the classification by substitution, right? So this is the reference. So that is usually your Hartree-Fock picture, and this is your wave function, the full wave function, and this is the singles, doubles, triples. So this is the Slater determinant, which says that you are exciting an electron from ith orbital and you are placing that electron in the virtual eighth orbital. And here you are simultaneously exciting the electron from I, placing at B, A, and J, placing at B. So this is the meaning of doubles and triples and so on, right? And if you take the linear combination of this, you can get the exact wave function. So here is a pictorial presentation. So initially the electrons was here and it was being lifted here. So these are the singles. So you can take many combinations, like you can excite this electron, and you can get different singles determinant. And in the doubles, so here was two electrons, right? And you have excited to one of the virtual. You can also put one electron here, and you can get other doubles, right? So now here is a three hole here and three particle in the virtual space, and so on. And then they have quadruples excitation and all. Now, how to obtain coefficients? Variationally, this is the configuration interaction method. Find the coefficient which minimize the total energy, equivalent to diagonalizing the H in the basis set. This is a very important statement that is made here, that for the configuration interaction, you can find the coefficient variationally, or you can diagonalize the Hamiltonian matrix in the basis of determinant. That can be proved. So this is your home task that you can try, that you try to prove that if you minimize the energy variationally and if you diagonalize the Hamiltonian in that basis set, can you prove that the two coefficients are the same, right? Or many body perturbation theory. Treat the Hartree-Fock as a zeroth order solution and you expand the total wave function in terms of perturbation series and you get the E0 as summation of EI, E1 as E Hartree-Fock, right? So I think this is wrongly written. Actually, if you take the E0 plus E1, that gives you E Hartree-Fock. Okay, so E1 is not E Hartree-Fock. It's actually, so when the many body perturbation theory will start, you will get, this is basically your first order times the V and first order. So let's not worry about this. It will be taught in this course. So when you take the E0 and E1, that gives you Hartree-Fock. That's why you go to the second order at least. Right, so then there you'll see about the many body perturbation theory, second order, and all that. So yes, and so then there is the configuration interaction, usually truncate. So this is very famous, CISD. You take up to singles and doubles, and it scales to 10 to the power 6. I have already discussed the scaling problem when I was discussing the slides given by David Sherrill for the Hartree-Fock. There I have discussed that for what is this term scales as 10 to the power 6 means, like this is a number of bases. And this CISD, you can see that if you incorporate a triple, your scalings, like it's basically killing, right? Now, why there is no CIS, right? So that we'll be discussing later. Now, so these are the Slater rules, configuration interaction matrices. Okay, um, I'll come to this when I'll solve that question. And you can see, so this is the Hamiltonian in the configuration interaction or the n electronic Slater basis, right? So this is HSS, then HSD, H, this is H00, this is H0S, H0D, and so on. Now, why these terms are zero? So you already know that you have been taught that the Slater rules. This is the identical determinants. This has already been taught, and where the determinant is differed by one electron, so one spin orbital. So here it was n and here it is p. So this is the formula that you already know, and this is the formula that if they differ by two spin orbitals, and if the determinants they are differed by two spin orbitals, that goes to zero, right? That is already been taught. Now look at this table. Is the percentage correlation energy, that is, so let's say you have a basis, you are able to so you are given a one electronic basis and you are being able to calculate the full CI correlation energy, right? Now if one truncates up to doubles, how much percentage of the correlation energy is being uh, recovered? So let's take this example, H2O as a equilibrium. So the equilibrium bond distance of oxygen and hydrogen. So if you see that the 95% of the correlation is energy is being recovered at CISD level. And if you go to CISD-T, it's 95%, and CISD-T up to Q, it's almost 100%. So whatever so in H2O uh, uh, there are 10 electrons, right? So there are a huge number of other possible configurations is possible given on the basis set that they have used. So if you take only Q up to Q, then you can, at least you can say that you have recovered 100% of the correlation energy. Now, if you see that the correlation becomes important, now 1.5 times Re means you have stretched the bond, so 1.5 times than the equilibrium bond distance. So now if you see that at CISD, it recovered around 95%, but here it is recovering up to 89%. So this emphasize the fact that as a higher bond distance or the away from the equilibrium bond distance, your higher order determinants play a crucial role. So from 89 to 91%, right? And at so if you increase that twice, then you can see only 80% of the total correlation is CISD. Even at CISD-T, you get the 84%. You have to include at least quadruples, and this is not possible beyond some molecule, right? So you need to do some improvement, and there you will see many methods are there. So this is one of the illustrations, and this is the again the CI space versus the excitation level, like how much determinant you are taking care. For example, see, these are very small molecule, BH, H2O, and I don't know the basis set. Maybe if I go to the paper, so I'll check that what is the basis set, and I suspect that the basis set is also very small. Uh, I don't know whatever the basis set quality, double zeta or triple zeta, whatever they have used. But so as a 6 electron, here is a 10 electron, 10 electron, 10 electron, and I think 6 electron. So you can see that there is a, at max 10 number of electrons is being correlated. You can see at at for NH3 molecule at full CI level, you have around 1,37,000 of the total configurations. Now, if you take uh, so so let's talk about H2O because we have discussed that. So here you have around 2,56,000, right? If you take up to 361, only 361 determinants, you can actually you have been able to recover 95% or 95% of the correlation. Or if you take a 3000 configuration state function, so I think which will be less than some what percentage? 3000 by, so which will be very near to maybe 5% or something. So then you can see that you have been able to calculate around 98% of the correlation saving. So this huge number of determinants, they may not be required for the chemical problem that you are interested in, right? Now this is the different thing that I'll not discuss here. Maybe I think in the course it will be discussed that what is size extensive, why a truncated CI method is not size extensive. That maybe we can discuss. Then again, the many body perturbation theory that will be discussed. And as you can see here, yes, E Hartree-Fock is basically this. So that was mistake that was there. Yes, that will be taught. Then the couple cluster theory. So what I am planning is that I think the couple cluster theory won't be discussed in that detail, but I don't know. If it's not, then I can discuss more on the couple cluster theory. Many body perturbation theory, MP2 will be discussed in a very thorough detail. And so when these things are done, we can start from here. But as of now, let's stop it here. I think you got very pretty idea that what is the number of determinants and what percentage is basically important and how much the costly of going to full CI level, and you cannot correlate beyond 10 20 electrons in today's computer. So there are very limitations to that. So how can one get better approximate method that you will be taught in the next week's lectures. So these are the rules that is being discussed. And now let's talk about this problem. This is very simple. So they have asked up to you take up to triples. So your total wave function is become the phi 0 and the summation actually, the singles over singles, C doubles doubles, and C triples triples. So you are truncating here. So there were many terms, but you are truncating here. Okay, I will not consider these terms. I will consider up to triples only. So there is summation. You are taking uh, all the singles, doubles, and triples determinant. Now let's write down the interaction matrix. So if this is your basis set, so these determinants, so you can write the total Hamiltonian in this basis set. So let's write 0 S D T 0 S D T. So this is your H00. That means psi pi 0 H pi 0. And what was that? That was your E Hartree-Fock, right? H00. All right, H00. And you can write here H0S. So this is basically the phi 0 H and the singles. I'm writing as H0S. And you have H0D, H0T, and so it will be HS0, HD0, HT0, HSS. So let me write down all the matrix elements here. This will be HSD, HST, HDS, HDD, HDT, HTS, HTD, HTT. So this is your interaction matrix. Now, I think from the Brillouin's theorem, you have already learned that if your reference is psi Hartree-Fock or phi Hartree-Fock, then your Hamiltonian is decoupled from the single space. This is basically zero. That is from the Brillouin's theorem. I think in the lecture it is already been proven that how it's coming out to be zero, because the virtual space and the occupied space, they are orthonormal, and you can prove it very easily that when this is the phi Hartree-Fock HS, these matrix elements are actually zero, right? So uh, if you have any problem, we can prove it. There is no problem, but this is the one of the information. So actually, this term, and this term, they will be zero. So you have a zero and zero here. Now this is zero D. So there is a difference between two spin orbital electrons. And what about this zero T? So there is a triple excitation. And from the Slater rule, you have already noted that if there is a difference of two electrons, more than two electrons, so that will be also zero. So this will be zero. So similarly, this fellow, this will also be zero, right? So, and however, these singles and triples, here you can see there is a There might be some elements that will be zero, but you cannot say that the whole block will be zero because there is a only difference of two. But yes, there will be some of the elements that will be zero, depending upon that whether there is a three spin electronic, the spin orbital difference or not, right? And I do not see any other simplification here. So yes, so this is the your interaction matrix. Now, what is the dimension of the matrix? So what do I mean by the dimension of the matrix? So this is a sum. I should not use n by n. So let's say it's a sum m by m matrix, depending on the size of the this total determinants. What are the number of total Slater determinants it has? So what will be that number? So the dimension of the matrix dimension will be 1. That is for your Psi-Hartree-Fock. And how many number of single determinant you can form? So let's say you have a n occupied space and n virtual space, right? So you have a n occupied and you have a n virtual. So you can actually n occupied C1, n virtual C1, right? So you can put actually electrons, this many electrons. Just a minute. Yes, so this many number of, this is the dimension of your single space. So similarly, you can, so in n occupied C, you can take two electrons from n occupied to n virtual 2 and triples n occupied C3, n virtual C3. So this is the total dimension of your matrix, right? So this is the dimension, or you can say this is the m. So then yeah, you will get a m by m matrix, right? So now we have already proved this Gaussian product theorem. Yes, so there are some other problems. It will take some time, so maybe it will be also lengthy. So I'll request you to try to solve this problem at your home, and in the next class we'll solve this problem, right? Okay. Okay, thank you.